Hello, thank you for joining us today. My name is David. I'm one of your IEEE Solid State Circuit Society staff members. This webinar is being recorded. We welcome you to November's webinar for Young Excellence titled The Future of Computing Systems Design. Just a reminder, we will hold a Q&A session at the end of the presentation. Please use the chat or Q&A section on your dashboard to ask any questions. The webinar video will be posted on the SSCS YouTube channel within a week, so please share it with anyone who couldn't make it today. I now invite Fei to give a few welcoming remarks.
All right. Thanks, David. And hello, everyone. This is Fei Guo from Shanghai Jiaotong University. I'm also a IEEE SSCS Young Professionals Committee member. I'll be the moderator for this webinar today. Before we kick off the webinar, I will start with a short introduction of who we are and what we do. So as young professionals and students, you make up for more than 30% of our overall membership, and you are the future of IEEE SSCS. As a SSCS Young Professional Committee, we strive to address the different needs and the interests to our younger members with initiatives like this webinar series. The selected IEEE SSCS membership for young professional members includes the following. For example, access to the SSCS Resource Center, distinguished lectures in your local settings, or having the opportunities to apply for different grants and awards, and developing leadership skills and make professional connections by becoming a local or global YP leader. Recently, we also had this online mentoring platform, which helps you to connect with mentors around the world virtually. So we also have physical mentoring events at our major SSCS conferences. Please stay tuned for the upcoming events. So since 2020, we have hosted webinars for Young Excellence, which is a quarterly webinar series dedicated but not limited to young professionals members. Currently, there are 7 of us to operate this webinar. The webinar series also complements the monthly technical webinars, which focus on mainly the technical developments. So the list of webinars we did in the past is shown here. These webinars are also available on the SSCS Young YouTube channel. So without further ado, today, as part of the webinar series, it's my greatest honor to introduce our speaker today, Professor Giovanni Micheli from EPFL. He will be speaking on the future of computing system design. Let me just give a short introduction to Professor Micheli, who also goes by Nanny. Is a researcher, well-known researcher in electronics and computer science. He's also credited for the invention of network-on-chip design automation paradigm and for the creation of algorithms in all kinds of EDA tools. He's currently a professor at the EPFL. Previously, he was also a professor at Stanford. He's a fellow of ACM, AAAS, and IEEE, and many other well-recognized organizations. He has authored over 900 technical publications and has been an author of many classical books. So today we'll hear Professor Micheli's insights on future computing system design. So welcome, Nanny, and thank you so much for being here. And we are excited to learn from you. Now you can start your presentation.
Good morning or good afternoon, wherever you are. This picture does not show really the future of computing systems. Actually, this is a picture of an art show in northern Iceland, not too far from the North Pole. I thought it was interesting just to show as introductory slide. So this is where I work. It's in Lausanne, Switzerland at EPFL. Lausanne is mainly known for the International Olympic Committee. The fancy building is the IOC building with the circles that actually shows the 5 continents all together and all linked together. I would like also to mention the Olympic motto, Citius, Altius, Fortius, and Communiter, because this relates to what I think is the system on chip motto. Citius means faster. We want chips with higher performance. Altius means higher, and we're going in the direction of 3D integrated circuits. Fortius means stronger. That means doing effort with less energy consumption. And finally, communiter means working together, integrated, using different teams in the world to come to a global chip. Having said this, we are facing many challenges nowadays. Here you see a picture from above of the world, and clearly one biggest problem is global warming and climate control. On the other hand, we have a proliferation of data center, computer centers that actually produce a lot of heat and actually consume a lot of energy. The market is mainly driven today by the AI ML applications, and so one issue is really the large amount of computation, of energy for computation. And we have to rethink architectures, circuits, and devices to make sure that AI is sustainable, so that we can use AI on edge devices, and also we have to curb the energy consumption. The picture on the right shows actually one of 3 Mile Island nuclear reactor that is being revamped and reactivated just to feed one data center. One data center consumes more or less the amount of energy that is taken by a power plant. So it's scary if we look at the trajectory of the needs that we have in terms of computation and the corresponding energy consumption and CO2. So it's important to find, of course, a human dimension of AI ML. AI is all over. Just to make a short announcement, in Switzerland, we just opened the Aperture Swiss LLM, which is a joint collaboration of the various schools. But my talk is not on AI ML because I'm not an expert in this, and I like more to come back to the global issues of computing systems. So what is design? Design typically it's a cyclical process where you go through various steps, let's say modeling, synthesis, physical design, verification, simulation, and back. And it's important to achieve design closure, which is actually done by iterating through the various steps in order to improve the figures of merit of our design. Typically, they're called PPA, power, performance, and area. But what about when there's no closure? What about when we push the limits of the desirable feature of our systems and we cannot solve the problem that we have? That's one reason why we look at emerging technologies. We look at novel circuits and architectures that actually can let us go beyond the limitation of performance and energy that we have today. So we have to reinvent the design in different directions according to applications. And part of that actually gets implemented in the creation of accelerators that speed up computing and storage. Now, in all this, design automation is the enabler for doing design and doing redesign and going across various technology generations and allow a rebirth of computing, that is computing in a different setting that in the future hopefully will be sustainable. Now, I'm going to touch various issues in this talk. I like to be broad, so I like for 1 second to look beyond technology. Advanced design and manufacture requires a plurality of efforts. We need competence, we need collaboration, we need critical thinking, and the future of computing clearly depends also on global politics and economics. It depends on the geostrategic alliances, and on the globality of the markets, because it's important to have large markets in order to afford new upcoming manufacturing processes that are expensive. Another very important factor is the presence and the tradition left by key visionaries that actually help to shape the future and their ability to attract and retain engineers. Along this line, I like just to mention two people who left us recently. One is Robert Brayton, who was at UC Berkeley, and the other one, Dave Liu, who was in Taiwan, and both have been big mentors for me and for various generations of engineers. Speaking broadly about the issues that we have, I like also to make tribute to Konosuke Matsushita, who was the founder of Panasonic and who's credited for the motto peace and happiness through prosperity. This motto later was changed into peace and progress through prosperity. The three concepts, peace, progress, and prosperity, are strongly related. There is a circular dependency, again, in PPP. But what I like to state today as key point number one of this talk is that we want to achieve progress through peace and prosperity that are two necessary ingredients in order to go further into computing design. First, because progress in any major improvement in computing, we require a large effort. We a large effort of teams that can be distributed around the world. We need cooperation. Cooperation is essential to pool exceptional talent. We can go forward only by having people who are very well prepared and who typically come from various parts of the planet. And also, we need broad markets in order to make the volume for affording advanced chip manufacturing. At the same time, it's important to have prosperity. We need to have support to retain engineers with good rewards. The rewards are not necessarily only related to salaries, but they are sometimes related to ability to tell engineers that they can explore new directions, be creative, not just follow orders. And I think this is an extremely important for us to remember. Now, let me switch gears and let me talk about technologies, the inside. This is a picture from a movie of Charlie Chaplin. Charlie Chaplin would have been a neighbor of mine. He lived in Vevey, but our lives did not overlap. And he did a lot about, telling people about how they should interact with the world, with the machinery, and with the changing scenario that we have around us. Now, if we move this into our problems, we have a changing scenario because we have new technology. We have moved from FinFETs to nanosheets, fork sheets. Eventually, we'll move to CFETs that are sheets of N devices on top of sheets of P devices that are on a vertical stack. This is a picture that gathers together the potential roadmap extensions. As you probably know, there are always tensions about the people who say, well, Moore scaling will never happen, or Moore scaling is still going to happen. This is the optimistic slide that shows us that we will be moving from the nano 2 node to the A14 node and beyond, where A14 means angstrom 14, which is 1.4 nano. But if you look at the picture below, as the technology of the devices progresses and gets more vertical, the shape of the gate stack changes because of the devices being smaller and because also of the metal pitch and contacts being different. So we already achieve a certain degree of verticality with these devices, and then we have to think of how to achieve design with this technology changes. It's not just that the devices are different, but it's a different type of paradigm for designing. And then you have to keep in mind that CMOS, it's not all. There are new emerging technologies that have been proven to be effective. These slides come from a design that's been around for about 6 years, and it's a RISC-V processor done with CNFET technology. CNFET means carbon nanotube FETs. These are transistors made by carbon nanotubes that are rolls of graphene, in simple words. What is interesting about this technology is that the devices have an inherent mobility that it's higher, and it also that it requires lower temperature and therefore enables manufacturing that stacks various layers. Here you will see in the picture on the top right that you have various layers, one corresponding to the end devices, one to the P devices, and the other ones to the interconnect. So even though this technology is emerging, it has been proven to be useful for designing devices with chips with 100K transistors and being able to scale up. It's also important to keep in mind diversity of the technologies that can come together. Various technologies can be combined in order to achieve acceleration of computation and communication. Some examples are here. Here we see again CNFET carbon nanotube devices done at MIT. Here you see a phase change RAM on top of silicon done at IBM. Here you see an optical chip to do matrix vector multiplication. Here you see another technology which is called MOS2, that stands for molybdenum disulfide, that also can be extremely interesting to build fast transistors and to build blocks that can enable fast matrix vector multiplication. And here you see some superconducting device done at Lincoln Lab. Now, looking at all these possibilities, which I don't want to cover, I like just to highlight some direction. Feynman said the famous sentence, "There's plenty of space at the bottom." By this, he meant that you can build devices that do computation using matter, and this has been kind of the beginning of the idea of quantum computers. Now, quantum computers are there today. They can be used in some domain, not to solve all the problems, but some domains that are extremely relevant. We have to keep in mind that quantum computers of today do not have error correction yet. And so those are called noise intermediate quantum computers, and are extremely useful in solving physics and chemistry problems. We are going to see over the following years to come a transition into the so-called fault-tolerant quantum computers that, because of error correction, will be able to solve important problems of combinatorics. But we are not there yet. Now, the big question is whether quantum computing will be just provided as a service by the major company that provides servers, or will quantum computing reach the workplace, the home, the edge devices? We don't know. Think that back in the 70s or the 80s, computers were just left in the big enterprises, were not at home. It was only in the 80s that people started bringing home personal computers. So we don't know what the future will tell us in the terms of the applicability of QC of quantum computing for our personal problems. Now, in quantum computing, you have to keep in mind that there are two aspects that are complementary and that are extremely important. One is the physical world. You do computation by using matter and by using property of the matter, including superposition and entanglement. But that's not all. You need in the design of computing system, thinking of how you map problems that are relevant into the quantum circuit that is the assembly code for quantum computers. And this requires a process which is called quantum compilation. That's the mapping of the high-level spec into these quantum circuits. Now, electronic design automation can be very instrumental for R&D in both domains. For one side, for advanced physical design of the quantum chips, and also for doing quantum compilation that will be very similar to hardware compilation done today for silicon, just to map these high-level models in languages or in flow diagrams into the quantum circuits. Now, I claim that there is also plenty of space at the top. What we mean by top, this is the physical top that's on top of circuits. Now we have circuits that are designed where we have transistors at the bottom and we have layers, sometimes 9 or 10, of metallization, and not much is done in those metal layers. Now we have incredible chances of working by putting special devices that could be FETs, that could be memories, that could be oxide RAMs, that could be memoristors that will be in the so-called back of the line BOL layers, and therefore enhance designs that are already done with scaled down technologies by having an additional layer for computation. So that's very interesting application, and here I'm citing research done in Germany, but there's also a lot of research done about the BOL all over the world. This picture here actually relates to the fully sequential integration in CMOS that shows actually transistors done in silicon technology, one on top of the other. This is extremely challenging because of temperature, and that's why by using materials that are different than silicon, it's easier to stack on each other. But today we don't see the stacking just done at the device level. Most stacking is done at the level of chips. We talk a lot today about chiplets, and the notion of chiplets is that you divide the functionality of large chips into smaller pieces, and then you realize different units, and these different units then on smaller chips that are less expensive and easier to manufacture and to test are flip chip and put on top of interposer. And this is a technology that's actually taking place a lot today. The next direction that I like to mention is that we have a lot of space in the cold. This is the picture that I took on the Arctic Ocean a few years ago, and it's just to depict this transition that we might see from bringing devices to cooler temperature. We've been seeing chill CMOS, that is CMOS working at 79 Kelvin, but now actually we see the opportunity of doing circuits in the superconducting domain. This is the superconducting electronics. We have two advantages there. One is that if you go at low temperature, let's say 4 Kelvin, you don't have the parasitic resistance. So the RC delays fade away. The second is because of the quantization of the magnetic field in the superconducting domain of operation, then you can transmit information with pulses that are quantized and they're pretty small, like 2 millivolt times picoseconds. Keep in mind that dimensionally this corresponds to a flux. That's why these devices are called single quantum flux devices. With these devices, you can design using a classic computing paradigm and have it gates that are deeply pipelined. And you have many variables or many variations of these technologies, and all of these are very interesting, even though all these are not yet so practical to be done at scale. We have example here of chips done in superconducting SFQ in Korea. This is a chip done in Japan that using adiabatic quantum superconducting electronics. Now, the advantages are very striking if you look at the energy delay product. Single flux technologies consume much less in terms of energy as compared to CMOS. And if you go to the adiabatic operation for these devices, like done in Japan, then again the EDP is smaller and gets closer, even though we are still three order of magnitudes away, we get closer to the final quantum limit that you have for computation. So that's extremely interesting when we look at, scaling up the performance energy spectrum of chips. Overall, superconducting electronics is good because it can be a support for ultra-fast acceleration. So to build general purpose accelerators, also for AI and ML, it has limited power consumption, even though much of the energy gets spent into the cooling of these devices. Superconducting electronics can also be used as a bridge to quantum computing processor because quantum computing requires hosts, and hosts are typically done with standard technology on silicon, and then the information can be transformed to the quantum chip in a way in which you can do control of the quantum chip, and superconducting electronics can work at this intermediate temperature of 4 Kelvin, which is good enough to do control of quantum computing processors. But on the other hand, in order to design with superconducting electronics, you need new EDA tools because these devices have to be highly pipelined, and they are also very sensitive to fan-out loads because the signals that they carry are small and therefore fragile. There are activities in China, Japan, and USA for superconducting electronics. This picture here, which is a painting of Salvador Dali called Fire, 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 shows us that there is not much space in the hot. The heat is the limitation that we have today for computing. Actually, I would say that the thermodynamics of computing system is the limiting factor. When actually you look at big data centers or centers that actually apply massively AI ML algorithms, then the issue is how much energy you bring in terms of amps, in terms of power, and how much heat you can actually extract out. Now, of course, there are many ways for searching for energy efficient computing. This type of research has been going on for more than 30 years, but keep in mind that it also involves kind of different type of approaches. One is to use reversible logic, which has been used in quantum computing, and nowadays there are scientists who try to apply this to silicon, CMOS. And then adiabatic computing. Adiabatic computing is a form of computation in which the clock in which the power supply is transmitted in the shape of a clock that is time varying, and it allows to charge and discharge capacitors with a limited voltage drop and therefore consuming less energy. But overall, computing systems are still very low in terms of efficiency, and therefore heat and CO2 generation per combinational task is still much higher than what we should expect. One important aspect is look at techniques that bring us to circular thermodynamics in computing. And I'd like just to mention one project that's happening in the center that I am directing in Lausanne that it's called EcoCloud. The project is called Heating Bits, And the idea is that we want to use the heat generated in water-cooled servers to produce electricity. How that is done? Well, you have data center with servers. These servers are water cooled. Water comes out at about 80 Celsius, and they will go for a heat exchanger where you have another fluid, which is an organic fluid that can boil and through a Rankine cycle can actually drive a turbine and generate electricity. Of course, the generate electricity from the heat removal is going to be much less than the energy consumed, but it helps actually increasing the overall efficiency of computation. As key point number 2 of this talk, I like to stress the diversity of architectures and devices. We've seen various technologies, various methods, and we have to keep in mind what is the competitive advantage of the emerging technologies. It's basically related to adapting the computational model to the computational fabric. New technologies can be useful, for example, to effect in an efficient way operations like operating on vectors of data. And of course, today there is a lot of interest in application-specific accelerators that are very desirable for both cloud and edge systems. And for them, what is important in order to achieve successful diversity of architecture and technology, you need both new computational thinking models and having new EDA tools and flows that let you design quickly with these new technologies in mind to create models and, of course, designs for these application-specific accelerators. Now I come to the third part of my talk. I will talk about design automation. Design automation has been around for about 50 years. This picture actually shows one of the first systems that were around 50 years ago that was a digitizer. At that point, people were drawing the layout of chips by hand and then digitizing them for mass making. That was a long time ago. What is important today? There are many important points in design automation, but what I want to stress is how design automation is done for heterogeneous systems. So how you do accelerator design. One important issue is doing high-level synthesis, that being able to do synthesis from behavioral specification. And the second important point is being able to connect seamlessly various computational units and chiplets. And it is done through a technology which is called networks on chip, by which you interconnect various parts in an electronic system using a technology which is borrowed from networking. Then what is important today is to synthesize computational elements that are both efficient and secure. Security is a problem that addresses all of us because we want to be, of course, safe about the data that we have and the data on which we compute. And this requires, of course, extending logic synthesis from the traditional domain to the domain of doing secure computation. And finally, what is important is being able to perform physical design for power, performance, and area, and support a variety of backends. And you need the flow completely from high level through networking, through logic synthesis, to physical design, sometimes even to explore the design space, because you would like to know what happens if you decide to use an alternative technology to do a component, a part, an accelerator of your system. I start by the assumption that we will not leave CMOS. CMOS will be the standard type of technology for system, but various parts may be convenient to be built with different backends. Let me say a few things about high-level synthesis, and today high-level synthesis has become a reality. So this is basically the mapping of models in languages for building FPGAs and ASICs. For FPGAs, that are many systems that actually use inputs in C or C++, that's been done routinely because people are used to programming software and they want to map software models into hardware models. But today also you can do that for ASICs. The new directions are extremely important. One is being able to address a variety of backends because you want to evaluate what are the technological choices within the high-level decisions. You want from a high-level model to do the what-if analysis of the choices of alternative backends. And also you want to consider a variety of modeling styles. And of course, in this case, you can leverage AI ML to explore the design space. Another technology which is important is networks on chips. I worked a lot on networks on chips about 30 years ago. And the notion is that on system on chips that are complex enough, where you have at least 100 computing core, now we have computing cores in the order of 1,000, tens of thousands and more, you don't want to connect them just through regular buses or wires, but you want to connect them through a network that interfaces the device to links and uses routers to transport the information around the system, much in a similar way in which we transport information in networks. Now, one important thing to keep in mind is that we are not using protocols like TCP/IP used for networking because they are far too complex. And in hardware, you want to have low latency. So the algorithms, the protocols for transmitting the information are highly streamlined for network on chips, are fairly simple, but still they're extremely effective and actually enable us to do scalability, how we can go to systems that are extremely large. And we can do that today, and network on chips are a reality for all large chips. More than that, network on chip enables us the ability, gives us the ability to separate various domains in a system on chip, and therefore having tunable power, tunable frequency on various blocks, because we can have different voltage islands where you have different clocking frequencies, and data can still travel through various blocks, and the links actually can adapt the information flow to that. And this is extremely important to lower the energy consumption of design. And more than that, with network on chip, it is much easier to do design closure. Design closure is the nightmare of all designers for large chips because you have to come up with a design that satisfies the spec. And if you network the various parts of the chip, you have fewer, shorter point-to-point wires, and therefore actually you have kind of a decentralized model of the system that's much easier to manage. And let's talk about logic synthesis. Some people tell me, that logic synthesis is a problem that's being solved. It's been actually tackled more than 40 years ago, and we have tools. I claim that there is still a tomorrow for logic synthesis, that not all problems are solved yet. I'm using this picture from a famous Italian movie that came out a few years ago related to the right of women to vote. Now, what am I claiming is that the main fabrics of most chips is a connection of logic gates. That's what we see in most chips. And we know a lot about logic networks and synthesis, But actually, a lot of the things has been written and rewritten. And I would like to point the interested people to one of the latest book of Don Knuth, which is the volume 4A of his classic Art of Computing Programming, that's actually related to logic and discrete mathematics. And there are very interesting points about logic design. Now, the important point is that there is more that we don't know than what we know. And some people object to that and say, is that relevant? Is it relevant to see the far side of the moon? We can design chips. We have tools that let us design logic. So why do we want to do that in a different way? Well, we care because we don't know how far we are from the best design. And we may be under designing chips, and we may have been doing that for decades. Actually, interesting, Donald Knuth said in his book that majority logic is probably the most important ternary function in the entire universe. I think Donald makes the things a little bit bigger by thinking of the universe, but he says that majority has amazing properties that are continuously being discovered and rediscovered. That is, technologies and techniques like doing majority logic were known in the 60s, but were systematized only in the last 10 years. What is majority logic? You have gates. These gates have an odd number of inputs, and they turn out a logic true if the majority of the inputs are true. Now, this can be axiomatized in math. The description of a majority algebra actually comes from median algebra. This is known, and this algebra has strong property like, for example, being sound and complete. But what's important is that majority logic can be represented with compact models. This is the majority inverter graph, where logic is described by majority gates that can be linked together by wires or by wires that have a bubble, the bubble being an inverter. So why is that important? Because once you have this model, you can have various ways of optimizing it. One is the algebraic rewrite model, by which you use axiom and properties of majority algebra to redesign the logic of your chip. Or you can use some Boolean techniques because majority builds in some sort of redundancy in the circuit, and you can use this redundancy to simplify blocks of the circuit that can provide some information that locally has errors, but these errors get corrected by the redundancy of the majority operator. Now, what is important here is that majority can improve commercial CMOS chips by 15 to 20% in delay as compared to earlier methods. And today, majority optimization algorithms are used within academic and commercial tools. And then, of course, majority can be used successfully for those emerging technologies where the majority gate is the native gate, like in the case of superconducting electronics or in the case of optical computing. Now, one important thing in this is also to look at issues that are important in circuits and often are forgotten in digital logic, which is looking at the difference and the opportunities of the analysis of the linearity. If you look at AND/OR logic, that's inherently nonlinear, and majority inverter logic, is also nonlinear. But we can discover and rediscover XOR gate that typically are not used much in CMOS because the gates are bigger, but these actually play a leading role in realizing adders and multipliers. And therefore, it's important to look at how you can do design, for example, by using XORs and majority gate. in which case we decompose the function into the linear part as done by the XOR and into the nonlinear part that can be done, for example, by the majority gates. Now I'll show you a very interesting thing by going through a quick detour. If you look at the majority inverter graph, this can be extended to the XOR majority graph, which is a model of the logic where you have XORs and majority gate. Think that an inverter is just an XOR with only one input. And in here, these gates have both the self-duality property. That is, if you complement the inputs, you get the complemented outputs. And also, these gates topologically can permute. That is, you can have XORs flow through a majority gate. That is, move the XORs from the input to the output of a majority gate. And this technique actually can be used in order to simplify logic circuits in any technology. But the interesting point comes here, that all the research done on majority and the use of majority and XOR came from the design of control polarity gates. These are gates done with nanowires in silicon, and these are gates where you have two control points. One is the polarity gate that makes a transistor a P or an N transistor, and one is a control gate that can turn it on. This is actually a micrograph of a chip, but with this type of technology, you can compactly design XORs and majority gates. Now, interesting enough, for this type of devices, about 15 years ago, we developed logic synthesis technique to leverage the combination of majority and XOR. And this was confined to this type of devices that are a little bit unusual and not much used today. But then what we discovered is that the same technique that used the XOR majority abstraction can be very, very useful for CMOS. And as I said before, in CMOS that can lead us to design that are 15% faster. And this brings back to this notion, which is important, of circular innovation. You start from CMOS, you go to a new technology, you develop EDA for the new technology, and eventually you go back to the EDA for CMOS. You come back the full circle, you reinvent the thing. This is a picture of the mythical phoenix bird that it's reborn from its cinders, its ashes, and it shows how actually you can have circular innovation in technology. Another important point, which I will briefly describe, is the role of multiplicative complexity. If you model circuits with a linear part, the XOR, and the AND gate, which is the nonlinear part, you have a very good abstraction for addition and multiplication. Now, the number of multipliers that you have in a circuit or AND gate are the multiplicative complexity, and the critical path of AND gates or multiplier is the multiplicative depth. Now, interesting enough, you take a gate, like for example, a majority gate, you can design it like this. You will find out that you need 3 AND gates. But if you design it like that, you will see that you can do majority with only 1 AND gate. This is the minimum amount of nonlinearity that you need in order to realize a majority gate. This concept actually generalized to the design of many circuits and finding in them what is the minimum amount of nonlinearity that is required. And many problems actually in logic synthesis can be done by analyzing what is the amount of linearity that you would need. Example is making circuit robust to side channel attacks. Another example for quantum compilation is minimizing the T cells, which actually are the gates that are most expensive in terms of realization for a quantum computer. And then, for example, in the case of security, actually reducing the cost of garbled circuits and improving the efficiency of fully homomorphic encryption can be related to the problem of multiplicative complexity. Now, I will briefly mention fully homomorphic encryption because today is a very important technique. This is just a picture of the Enigma machine. Of course, it was something that's old that has nothing to do with FHE. But FHE is the technology that enables us to compute with encrypted data. So the data is secure because you would transmit data that is not readable by other people. Now, it's the fact that we realize computation on encrypted data makes the computation more complex, slower. The first approach were 1 million times slower than the computation without encryption, and therefore it was not practical. Today, you can go down to 2 orders of magnitude in slowing down the circuit, but it's extremely important to have algorithms that allow us to design circuits where you reduce the multiplicative complexity and depth of circuits for encryption. Because when you do encryption, multipliers generate noise, and you want to reduce the amount of noise that is inside encrypted circuits. Otherwise, you cannot restore the information. Finally, a few more words about other important topics. I do not work much about physical design, but physical design is still a very challenging EDA task because in CMOS technologies are evolving with the downscaling, and if you look at other technologies like field coupled nanotechnologies, important issues are there. For example, the planarity and the wire crossing. Working in 3 dimension, it's important where you have anisotropic delays and where clock distribution is complicated. So I would say that in the future, success and showstops of emerging technologies will depend much on the ability of high quality physical design tools. And now, what is the elephant in the technology room? You see a picture of a good friend of mine when he got married, and I'm behind him on the elephant. But this is to say that the big elephant that we didn't mention today is the role of AI, ML in EDA. I didn't mention it because the results that we have today that are solid are not that many. We know that AI and ML can be applicable almost everywhere in order to speed up the algorithms and making EDA and design more efficient. But in the present day, AI is mainly used for design space exploration because you can tabulate previous design, you can compare, you can learn from previous design, and therefore you can achieve better design. I do not want particularly to talk much about AI because I think that most techniques that I use in EDA are borrowed from some other fields, and as I said, I'm not an expert in AI. But I would like to close this part of my talk by making my key point number 3, by saying that EDA, electronic design automation, is the enabler for future computing systems. And in particular, the AI ML application will require the design of novel architecture by EDA tools. And the EDA theory and practice must, of course, follow the evolution of the technology and incorporate the emerging technologies that we see today in prototypes. Now, synthesis will allow designer to reach multiple goals and improve on the PPA. Verification will be more and more essential, especially in view of new modeling methods that may involve using high-level models generated by AI where the 100% correctness is not guaranteed. So I expect verification to be more and more important in the years to come. Well, I've covered a lot of ground in this talk. I'd like to come to some summary and conclusion. The first point is that progress requires stability and international collaboration. This is especially important for the evolution of computing systems. Next, technically efficient computing systems need a match between architecture and technology, and this requires, of course, diversity, and accelerators are a mean to change possibly local the architecture of systems or blocks and exploit also the diversity of new materials and new circuits, topologies, connections, and so on. Next, logic modeling and reasoning is a fundamental tool. Logic design and logic synthesis not an achieved step. We need algorithms for diverse design that may leverage a wealth of techniques, especially in view of the fact that security will play a leading role in the years to come in electronic systems. And finally, the great news, chip design is entering a new exciting epoch. We are seeing really a resurrection of chip design, many requirements, many new needs, and this is really important to sustain the fast evolution of algorithms, software, and services. With this, I would like to thank you. I would like to thank my sponsors and show a nice picture of Lausanne, our libraries under the snow. Thank you for your attention.
Great. Thank you very much, Professor Micheli, for the insightful and inspiring talk. I think these perspectives are definitely enlightening, especially for the audience who are young and who are still students. I think we have some time for some questions. So for those audience, you can type your questions in the chat box, and I'm gonna read it out. So to start with, so here we received a few questions. The first question is that, so as you have mentioned in the slides, there are all these different aspects, that span from physics, materials, electrons, or software that can enable future computing systems. And then what blend of skills will be the most valuable for the students or junior engineers, especially in the IC design field, in the next decade, in your opinion?
Thank you. This is a great question. I think that my talk was about the renaissance of chip design. And I think that we need to train engineers with an open spirit, that students should learn a variety of topics, understand the fundamental, and not just be specialists. I think that, of course, you can opt to be, a specialist in digital design, great for doing the physical design in CMOS and so on. But I think that people who can make the most out of their education and make a dent, in today's science and technology are the people who will understand the trade-offs. The fact that you can use a technology, another one that you can use a trick and apply somewhere else. My experience is we build those devices that were silicon nanowires and we develop EDA for them. And in the end, all this EDA has been used for CMOS design, for standard CMOS design, but we figure out a new angle to tackle the problem. And so it's really important to have a rich education in various domains.
Yeah, that's very well said, and I fully agree. And another question is also interesting. So you mentioned a lot of these technical aspects, but in your opinion, what are the ultimate challenges or like limiters in the non-technical aspect that can kind of prevent the future computing system development? Is that the energy policy, public trust, or global cooperation, or something else?
Part of that is related to energy.
Hmm.
Data centers consume too much. I'm not particularly scared of the fact of using nuclear energy. I'm I'm not against it, actually. I'm in favor of it when it's needed. But the question is localizing the data centers. There are many areas in the world where you cannot build a data center because you cannot transport the energy there. And so that's actually something that we have to take into account. So again, where we can distribute our resources, not just for a green planet, but we need globally to think of where we can do the computing and how we can transport it. And we should also, that involves also global policy, because there could be places where energy is less expensive and where you would like to have a data center to just make more money, but where energy actually uses some sources that are more polluting than some others. So we should favor places for computation where you have lower cost and clean energy usage. And that is complicated. But I think that we really need, as a worldwide community, to think about this and work together.
Yep, I agree. I think collaboration is very important. Yeah. So another question is that so now we are everyone is talking about AI, and also all the EDA tools are like fused with all these different AI techniques. And then with so many AI components, are we raising a generation of drivers who don't know how the engine works? Because most of the AI are like black boxes, right? How do we actually teach the engineer intuition behind the automation then?
Yeah, it's difficult. I'm trying in my EDA course to make them use some AI tools, but these are black boxes and you don't learn
Yeah.
anything. And another thing that's dangerous, if you use AI tools to synthesize high-level models, and this can be handy, can be fast,
Yep.
but since you don't do the thinking process, there might be some bugs. Of course, the bugs can be there, but it may be extremely difficult to find the bugs because you're not the person who has created the system.
Hmm.
And so it is, um, and chip design is a domain where the things have to be 100% correct. If you have just one fault, one malfunction, then what you've done is useless. And that is a big problem. So, we have to learn to use AI to support our thinking process, but not stop our thinking process. Otherwise, that it's probably not going. We can gain in the short term, but at some point we'll get stuck.
That's true. There's always a trade-off, I think here. And another question is that since the computing systems are becoming more and more powerful and specialized, then are we risk of creating a computing divide where only wealthy corporations or nations they can afford the most advanced computing systems or can have more research capabilities?
Uh, yeah, that's another question, the fairness, of
Yeah.
giving computing. Uh, One of the first fairness thing that's been discussed around the world was to make sure that people had enough to eat and or have enough water. There are still some countries in the world where some people don't get water.
Right.
And I wouldn't just make examples, but I've been in places like this,
Hmm.
and it's terrible. And we have to provide also the ability to people to do at least some computing. Um, but the trends can be a little bit scary because until now, we had a very nice free ride because the downscaling of technology corresponded also to a downscaling of cost. That's why the people actually downscale CMOS, because they make more money. And we have all these gadgets and all these consumer devices that we have, the telephones, the computers, the TVs, actually help making electronics cheaper. But at some point, I think that scaling will not make the thing cheaper. And so only those who will really require high performance computing, and unfortunately, that will be defense, that will be science, those people will afford then the high end. And that is dangerous because then it's going to split the community.
Yeah, that's true. Um, And another question is that so since the power density continues to rise, you also mentioned there's a huge need for the new cooling techniques. And then if we need to consider cooling, then what kind of role the system architects need to play in even co-design with the cooling solutions in the mind? Are this going to be also part of the design methodology or like considered in the earlier design phase by taking consideration of the cooling?
Well, of course, part of that relates to the design of stacked architecture like chiplets, and now people
Mm-hmm.
can do microchannels in silicon and having fluids that go through for doing some local cooling.
Mm-hmm.
Uh, all this in the end has limitation. If you look at, when people project new data centers and new racks, the question is how many kiloamps you bring into rack. It's extremely scary how you would do that, and what will be just the power loss along the wires and the cables that bring electricity down. Um, so of course there will be trade-offs among how we do, dense computation, how we'll try to spread it, how we can use parallel computing in a better way. That I think is still a problem that we have always tackled and never really solved. What is the optimal way of doing parallel and having, parallel distributed faraway components so that the heat is not too much.
Mm-hmm.
And then, of course, in the future, the use of also as hydrogen as a way of creating locally energy to feed the computation, and also creating water as a byproduct that can be used also to cool. These are things that are really open-ended, but could be very interesting.
Yeah, yeah, thanks. Um, yeah, I think due to time limit, so we'll leave time for just one final question that we ask for all the speakers. Um, so since you have vast experiences in the chip design and EDA and all the industries, what are your words or advice to the young professionals or next generation engineers who are in this field?
Okay, my suggestion is that you do this job because you're having some pleasure, some fun. I still have a lot of fun to work, and be broad, talk talk to people, look at what are the problems, don't get stuck on one way, on one method, communicate, go to conference, have in-person connection, uh, because those are much better to get ideas, and be open to changes, because things change so much over the last years, and we might find new materials or new technologies that can change again everything. So we are not on a stable trajectory, but we actually can see a multiverse of solutions in the future, and that's actually very challenging and very interesting.
Yeah, thank you very much. Well said. Yeah, as I mentioned, due to time limit, we have to cut here. And on behalf of the organizing committee, I would like to thank again Professor Micheli for spending time and share your insights and perspectives on this very important topic. So as noted earlier, so the recording of this webinar will be available at the SSCS YouTube channel. Before you all leave, don't forget to complete our feedback survey. And thank you again, Professor Dimichali, and thank you for the audience for attending this webinar. And have a great day. Thank you.
Thank you so much for inviting me. It was a
Yeah,
pleasure. Bye
thank you so
bye.
much. Yeah, thanks. Bye. Bye.